Hello, folks. I was back to working on my microscopy project again this week, and the issue of drift correction in our microscopy images came up again. Now, to recap this problem, what we have for this particular project is a series of microscopy images that were taken over time of defects moving around the material. I don't have the actual microscopy image on hand, but what I have here is a mask showing white regions where a machine learning model that we created detected a void in the material. And I have these over the course of time. And we'll scroll through a bunch. You'll note here that the voids, their position towards each other does stay relatively constant. The voids do move relative to each other, but what you're seeing mostly in the video is not that movement with respect to each other, but the gradual drift of the microscopy image because it's inside of a microscope, there's thermal swelling, the beam drifts, and all of these other factors complicate us from being able to see what's going on with the individual voids in their movement, and thereby allowing us to understand how materials change at the atomic scale better. So what we're going to do is talk through how we did this drift correction, and particularly a step that we added in and refined this week, where I take many different drift corrections made for the same image and combine them together into a single model that explains how this entire system is moving over the course of time. All right, so let's go back to the beginning. And this is actually something we covered in a previous video. The way that we measure the drift between two frames is using a technique called a fast Fourier transform. What I do is I take two images and I compute what's known as a autocorrelation plot that shows if I were to offset these images by a certain amount with each other, how much they overlap. And you'll see there's a real bright dot here, kind of not far off the center, maybe a little up and left. That is a position where if I shift one image by that amount, it lines up very well with my original image. So that gives me a measurement of the drift. And one thing I can do is I could compute the drift over the entire stack of images by going between each adjacent pair and measuring this drift, which is something I could totally do. And if I do that by measuring each of the adjacent planes, I can get a fairly reliable measurement of how this sample drifts over time. And you can even see where my colleague, who was at the microscope at the time, noticed the drift himself and adjusted the microscope to compensate. So you can see all of that in the data, which this is fantastic if I trusted this drift correction very well. Now, the problem is it's noisy. Not only is there kind of a possibility of multiple kind of explanations of what the best drift correction could be. That's one potential issue. There's also some noise added in here from the fact that these segmentation maps are created using a machine learning model and the idea that sometimes the true drift may be smaller than a pixel. So we can't actually resolve it between kind of two adjacent frames. Instead, what we could do is look at frames that are farther apart. That I could look, say, instead of next to each other, I could look every 5. And here I should have a more reliable picture because that drift is larger, and thereby I can measure it more accurately in theory. So that is one thing, and you could imagine I could build my drift over a function of time by computing every 5 and combining them together to form a time series. What we ended up doing was this, what we're calling a multi-reference point, where what I do is I compute the drift between each pair of images that are adjacent to each other, each that are every 2, that are every 4, that every 8, and I can use all of these measurements of drift together to form a single model for what I think the drift was over time. Now, the way I do that is actually using linear regression or linear least squares, the same kind that you might use in statistics. The way that that works is what I'm actually measuring here on this plot above is the relative drift between two frames. I'm not measuring their absolute drift with reference to, say, the first image. So what that does is gives me this linear equation. I have the drift of frame J, and I have the drift of frame I, and I'm subtracting them from each other to get a relative drift. Now this here is a linear equation, and if I get a bunch of these together, I know that I can solve the values of these two variables by combining all of those together into a single equation. So imagine it works a little bit like this, and I'll boost the font size on the spreadsheet here, that I've got, say, actual drifts of an image in 1D that look like this. What I'm doing when I'm calculating the relative drift is I'm taking one image and subtracting it from the other to get a certain value. And I can do this many different times through different pairs of images, yielding different relative drifts to each other, giving me a whole systems of equations. Now, to solve this is actually a little bit subtle, because these measurements here are not a fully determined linear system. I'm not measuring an absolute drift for any image. So there exists a multitude of values that I could explain the absolute drifts of each of these images together. So let's say image one, if this one I have 1 and 3, 2 and 4 and 6 would be give me the same results for the relative drifts, or for the relative drift between two frames, because 1 and 2 are 2 apart, 1 and 2 are 2 apart here, 2 and 3 are 2 apart, 2 and 3 are 2 apart, and so on. So if I try to solve this using the linear least squares that you learned in statistics class, it's going to balk. So here you can see the matrix equation for solving this. If I try to solve that in Excel, you'll quickly see that I get this problem, the matrix inverse is not invertible. Now that is because it's a underdetermined linear system. Fortunately for you, there are numerous ways to solve this. One way you could do simply is called Tinikov regularization, where I add in a little fictitious value that allows me to make that matrix invertible. What it's doing here is forcing another condition on my solution. Not only should it match the data that I've provided, but it should also minimize the values of these estimated drifts. So if there was a space of infinite possible answers, I want to have the ones where their absolute values are the smallest. That's how this kind of regularization works. This is a heuristic and it works, and there are actually a whole series of methods for solving these so-called underdetermined systems, which I didn't actually know a ton about until I started putting things together for this video. But suffice it to say, there are numerous techniques, and if you use a package like SciPy to do your solutions, they link into them. So you can see here, and I'll show you where this looks like inside of the SciPy source code. You'll note that it has a LawPack driver that defaults to a code called general ALSD. That's actually corresponding to a Fortran routine that solves, yep, here it is, that solves this underdetermined linear least squares problem using a numerically efficient technique implemented very well, which allows me to solve my linear systems of equation problem very quickly. Now you'll see that it took me 5 minutes to calculate the drifts, 5 minutes and 22 seconds. It incidentally took 5 minutes and 22 seconds to both assemble all of those relative drifts and then to solve the resultant system of linear equations. So I can speculate here that solving the systems of equations took less than a second. And then if we go to the source code, we'll walk back to the source code of this. You can see here the way that it works. I go through and here we are. I loop over and I compute the relative drifts between many different image pairs. I'm forming a big set of linear equations here. That's this matrix from the examples I showed you. I then go back and I call NumPy's linear least squares, which under the hood somewhere, it's calling one of these really well-established source code implemented in Fortran somewhere by someone who knows a ton more linear algebra than I do. And together that gives you the ability to calculate drifts very efficiently. So here you can see I get basically the same answer with my multi-reference drift point, and it does a fairly well job. You can see these images here are pretty far drifted from each other, and it aligns them up pretty well. There's still some issues. I probably need to tweak this algorithm a little bit more by selecting either fewer or more offsets to consider when calculating the reference points, but that will be a problem for another day. I've got at least the basic code together, and it's relatively fast. So I can try out many different opportunities. That's all for today. Hopefully this helps address the problem that you have now, or at least scratches the surface of knowing what's going on under the hood, underneath a software like NumPy. Hope you're having a nice day.